Okay, here we are with paper quiz 9, and we'll go ahead and solve this. The first question has you solving algebraically and then solving graphically using your calculator on this last one. So let's start with this one. 2 to the 3x plus 4 equals 5. Now, if 5 had been 8 or 4 or 16 or 32, we would have written the left side as a power of 2, the right side as a power of 2. But it's not so easy when we have 5. If you really were interested in something like that, you could write 5 as 2 to the log base 2 of 5, and then you could equate the exponents. Or probably even simpler is to take logs of both sides. Now, if we take, say, ln of both sides, we'd get something like this. ln of 2 to the 3x plus 4 equals ln of 5. And by one of our properties of logarithms, this becomes 3x plus 4 times the natural log of 2 equals the natural log of 5. And remember, the natural log of 2 and the natural log of 5 are just some numbers. So we would get 3x times the natural log of 2 plus 4 times the natural log of 2 equals the natural log of 5. And so, isolating the terms with the variables, we'd have natural log of 5 minus 4 ln 2 on the right-hand side. And we can see the coefficient of our variable is 3 ln 2. And so we would get that x is equal to ln 5 minus 4 ln 2 over 3 ln 2. And that would be a solution. Alternatively, if we were to take log base 2 of both sides, that is, rewrite this as a logarithmic statement, we would get a little bit faster to our final answer. We would get the log base 2 of 2 to the 3x plus 4 equals the log base 2 of 5. And one of our properties of logarithms says that these two cancel each other out, so we end up with 3x plus 4 is the log base 2 of 5. And simply subtracting 4 and dividing by 3 gives x. So whether you write x like this or like this, you have the same answer. And again, you could have taken log base 10 of both sides. All right, the next one, similar equation. Solve algebraically, and this one's pretty straightforward. We're going to solve first for natural log of x by subtracting 7 and dividing by 5. And then we can either raise e to the left-hand side and e to the right-hand side, so e to the ln x. And again, these are more mental constructs than they are actual differing techniques. So e to the ln x equals e to the 2/5. That is, if these two are equal, so should e to this and e to that. Alternatively, we could rewrite this exponentially, and we get that x equals e to the 2/5, fifth root of e squared. Doesn't matter how you do it. The next one we have here is to solve using our calculator. And for this one, what's important is we understand it's important we understand the limitations of the calculator. And so I'm going to go ahead and type in 2 raised to the x as my first function, and then I'm going to type in 2 plus ln x as my second function. Okay, and I'm just going to zoom 6. That's our standard window. We have one graph. There's the 2 to the x, and here comes 2 plus ln x. And 2 plus ln x is the natural log graph that's been shifted vertically up by 2 units. And it's hard to tell, but it looks like in there might be some intersection. I'm going to use the zoom box feature. And it's not exactly clear, but I'm going to go ahead and take a shot at trying to grab a hold of some of what's going on in there. Let's see what we see. Here's our 2 to the x graph. Again, it looks like there's an intersection there. Let me zoom out. Looks like there's 2 intersections. I'm going to take a shot at finding both of them. It looks like if I was to exaggerate our graphs, what I'm thinking is there's something like this. There's 2 to the x. And there is 2 plus ln x. I'm thinking that there's 2 intersection points. So I'm going to go ahead and see if the calculator can distinguish them. First curve, second curve, guess. Okay, I found one at x equals 1. So that's a solution. By inspection, we can tell that's an exact solution. You can simply plug it in, 2 to the 1, 2 plus the natural log of 1, which is 0. The other one, first curve, second curve, and then I'm going to try to go over here and force it so you can find another one, 0.6499. So it looks like we have x is about 0.6499. So those are our 2 solutions. And it's possible there could be more, but I'm going to just stop at those 2. So we took y1, y2, this is y1, and that was y2, and we use the intersect subroutine. Alternatively, what we could have done is we could have graphed y1 is equal to 2 to the x minus 2 plus ln x. And let's see what happens if we do that. Minus 2 minus ln x. Now here it might be just a little clearer that our graph actually dipped below the x-axis. Here we are with a couple zooms, and I think we can just see that the graph touches the x-axis at 2 different locations. And those 2 different locations, left bound, so I don't know my scale here. I'm not sure where my right bound would be. That should be x equals 1. And then using the 0 subroutine again, and we can go 5 pixels at a time. That's certainly a left bound. We're above the x-axis. And that's a right bound. And we get the same 2 graphs. We get something like (1) and 0.6499 using the 0 subroutine. Okay, moving on to the next one, which is to solve algebraically e to the x plus e to the minus x equals e. For this thing, the key observation is that e to the minus x is 1 over e to the x. This e out here is just a distractor. And if you notice, your variable x appears as part of the same sub-expression every time. So we're going to let w equal e to the x. If you can completely rewrite the variable aspects of your equation with another variable, this is called a dummy variable, like a ventriloquist dummy. It stands in for x, well actually a little bit larger than x, but it allows us to see that this equation looks rational. And so for this guy, I'm going to multiply both sides by the only denominator, which is w. And remember that e is just a number, so we get w squared plus 1 is we, or ew, if we write the coefficient first. In standard form, we get a quadratic equation whose coefficients are 1 minus e and positive 1. And so according to the quadratic formula, we get the opposite of b, which is the opposite of minus e, plus or minus the square root of some stuff, all over 2a. b squared is e squared. 4ac is 4. So we get our solutions for w in this case. Now w was a dummy variable, so whatever w was, we're going to let it pop back up, and so we have e to the x now is equal to these two numbers. And then rewriting this logarithmically, or equivalently taking natural log of both sides, we get x is the natural log of this. Again, a to the b equals c. This would be b equals log base a of c. And it's good to check that both of these are strictly greater than 0. Okay. All right, let's check the next page. Another equation to solve algebraically. The log of x plus 1 plus the log of x plus 2 equals 3. You should be able to do this on your calculator, verify which solutions there are. You would, for example, set y1 equal to the left-hand side and y2 equal to 3 and look for intersections. But we're asked to solve it algebraically, and remember that that means we're looking for exact solutions, and our calculator rarely gives us exact solutions unless they happen to fall in very nice numbers. So our first thing is to realize that these two logarithms can be combined into a single log using one of our properties. And now using our ABC, log to the base a of b equals c, we're going to rewrite this as a to the c equals b. That is 10 to the 3 equals x plus 1 times x plus 2. So we get 1,000 equals x squared plus 3x plus 2, or in standard form, x squared plus 3x minus 998 is 0. And again, quadratic formula. A is 1, B is 3, C is... I would give myself a few seconds to try to factor that, but really that 998 looks a little daunting. So we have our solutions would be opposite of B plus or minus the square root of some stuff all over 2 times A. B squared minus 4AC, I'm going to do that in my calculator. B squared is 3 squared minus 4 times 1 times negative 998. You get 4,001. So 4,001. And the numbers here, minus 3 minus root 4,001 over 2 is negative, and minus 3 plus root 4,001 over 2. And if we were to approximate these numbers, The square root's around 63, so negative 3 plus 63 is around 60. And over 2, that would be 30. Approximately 30. And negative 3 minus 63 is minus 66. So minus 33. The reason for this is when we look up here, we see that x plus 1 and x plus 2 have to be both positive for these expressions to be defined. And so x has to be greater than negative 1 and greater than negative 2. And we can see that this number fails. And that number is minus 3 minus. So I'm going to reject that. So the only solution is x equals minus 3 plus the root of 4001 over 2. Okay, indicating the exact value of the solution. Okay, in this next one we have a classic radioactive decay problem. The model or the function for radioactive decay here, and typically this is thought of as a relationship between A and T. That is, A is written as a function of T. P and K are just some parameters that deal with the individual kinds or amount of radioactive decay. So in our first case, we have 200 grams as our initial amount, and that's P. And we know it decays to 150 grams after 100 hours. That means that the amount present after 100 hours is going to be 150 grams. So 150 grams is the amount present if we start with 200 grams and we let this process run for 100 hours. And from this we can solve for K, which is our first thing. Use this information to find K to the nearest millionth. And so 150 over 200 is e to the 100K. And that's equal to 0.75. So if we take natural log of both sides, natural log of 0.75 is 100K. And so the natural log of 0.75 over 100 is K, which on our calculator turns out to be, let's see what it turns out to be. The natural log of 0.75 divided by 100 is minus 0.0028768,207, etc. And for our purposes, we're going to want to go to the millionth, which is 10 to the minus 6th, right there. That is the millionth place. And so we see that the digit to the right is 5 or greater. And so we're going to stop right there and raise it by 1. And we can check if we wanted to. The checksum would be 2 plus 8 plus 7 plus 7, which is 10 plus 14 or 24. And again, that's correct. If you had used units of days or minutes or something different, your K value would be different and the checksum would not have been 24 necessarily. So now we have our function. Our specific function is A of t, or A, depending on how you want to write it, is 200 e to the minus 0.002877t. That is what we have now. And we can use that for various things. So for example, how much will be left after 1,000 hours? A of 1,000 is equal to, and here's a good case of using our calculator. Go ahead and put this in. 200 times e to the minus 0.002877x. Again, we can't use t. And I'll go to a table. Let's see if my table's on automatic, and it is. So let me turn that off. And so let's see. We want to evaluate this at 1,000. And we get 11.261 or 11.260, etc. And we want to the nearest hundredth of a gram. 11.26 grams. The next question asks us, how long until half of the initial amount remains? Well, the initial amount was, remember, 200 grams. And how long until half the initial amount? That would be 100 grams. So we're going to be solving the equation 100 grams, or just 100, is equal to 200 e to the minus 0.002877 t. We're going to solve that for t. Now we can do that two ways. We can do it algebraically, or we can do it in our calculator. And to do it in our calculator, we would graph this in our window. Let's see. I'll start with time 0, and we'll run out to time equal to maybe, let's see, well, 1,000 hours gave us 11 grams. Let's try 500 hours, and I'm going to try zoom 0, see what we get. So this should be a graph of our radioactive decay for the first 500 hours. That looks pretty good. Okay. And if we were to draw a horizontal line at level 100, we can see very nicely it intersects our graph. And second calc, intersect, first curve, second curve, guess, 240.9 to the nearest tenth. Okay, 240.9. Okay, so on a calculator, we would do it like that. Let's go ahead and draw this out. Calculator, we had something like this. That's A of t. And this is time here. This is grams here. And we had, say, 100 like this. That was 200. And we see the intersection point turned out to be 240.9. Now, to do it algebraically, which we could also do, if we were to do this algebraically, we would divide both sides by 200. Take the natural log of both sides, or equivalently rewrite it logarithmically. And then divide both sides by the coefficient of t, which in this case is the k we had solved for. And we should find that it turns out to be very much the same number. So natural log of 0.5 divided by minus 0.002877, 240.9270701. So to the nearest tenth, 240.9, and this was hours. So, okay. Let's look at another one. Another one is this classic. Everyone's cooling coffee, but it works whether the thing is cooling off, heating up coffee or slushy or anything else, just a block of metal. So our first case is a cup of coffee, which starts at 150 in a room that's held constant at 72 degrees Fahrenheit. By the way, that's the environment temperature. After 45 minutes, it is cooled to 95 degrees, and T0 would be our 150. So this is 150, and this is our 72. So the difference between them would be 78. We're going to first find K. So let's go ahead and throw everything we have here. The temperature at time t, well, if we were to put in K equals 0, we would simply get T equals T0. That's, you can always check. At T equals 0, T equals T sub 0. That's the way this is constructed. So at T equals 45, and we'll use minutes, we should get, at T equals 45, big T should be 95. So let's see what we get out of this. 95 is equal to the environment's temperature plus the difference between the environment and the object's initial temperature times e to the k times 45. And we're going to try to solve that. So we might need some paper here for this. Let's go go ahead and try to solve that. So here, we're going to subtract 72 from both sides. You can't add these together. Remember, 78 is attached multiplicatively to this e to the k times 45. It's only added on this. So the order of operation says that we can't add the 72 and 78 together, but we can subtract 95 minus 72. So we get 23 is equal to 78 e to the 45k. And so 23 over 78 is e to the 45k. And so the natural log, again, rewriting this logarithmically or taking natural logs of both sides, there's no difference between them. You can either ABC it, a to the b equals c, or you can take natural log of both sides, or log base 10 of both sides. And dividing both sides by 45 gives us k, which is going to be, let's see what k turns out to be. So the natural log of 23 divided by 78 divided by 45 minus 0.27138. And we're looking for the nearest millionth. 27138, 27138, 1025. That's as many digits as I see here. And we want the 10 to the minus 6 or millionth. That one. And we can see in this case, we can simply cut it off or truncate it at that point. So this will be our value of k. And if we check the sum of the digits, just for the heck of it, the sum of the digits 2 plus 7 plus 1 plus 3 plus 8 should be 21. Okay, so we have our k value. Let's see what the next question is. What will be the temperature of the coffee after 1 hour? And our k, remember, depends upon minutes. So we have at this point that our temperature function as a function of time, big T as a function of little t, remember, is 72 plus 78 e to the minus 0.027138 t, and we want big T at 60. And I'm going to go ahead and enter that function because we may be using it more than once. So we have 72 plus 78 e to the minus 0.027138. Again, we use x. And in a table, I can simply evaluate that at 60 and come up with 87.3. So we have T of 60, which is approximately 87.3 degrees Fahrenheit. And we want the nearest degree, so it would be 87 degrees. So the nearest degree would be 87 degrees Fahrenheit. Okay, the next problem is how long until the coffee reaches 80 degrees. And there's two ways of doing this again. We can do it algebraically by solving 80 equals 72 plus 78 e to the minus 0.027138 t for t. Alternatively, we could take our graph, and let's see, again, the window is critical here. So let's take a window that goes from 0 to maybe, I don't know, about 500 minutes. Let's try 2 hours. And our, let's see, we'll do zoom fit. Let's see what we get here. So here's the coffee cooling. And notice our window has a y-min of 0. I'm going to go ahead and put our y-min of, you can see in this case, there's a horizontal asymptote here. This graph flattens out as the coffee approaches the temperature of the room. And let's see, we want to have it equal 80 degrees Fahrenheit. Let's see if we can fit that on our screen. Do we see 80 intersecting? Yes, just out here we can see 80 intersecting it. So first curve, second curve, intersect. 83.9 is our intersection point. So on our calculator, we have our graph. It started off at 150 and it's cooling off to a room temperature of 72. There's my actually big T of T, not A of T. That's my big T, and this is time, and this is temperature, right? And this time in minutes. And we see at 80, exaggerating it, we have an intersection of 83.9, approximately 84 minutes. Okay, so we have the solution is 84 minutes, approximately. And you can solve that in the same fashion we solved for K. If you remember when we solved for K, here, the variable appears in the same position. Okay. All right, now, here's a problem where an oil spill, say it's circular, starts off at 25,000 square meters in area and grows by 2.4% every day. Find the following, rounding our answers of area to the nearest 10 square meters or to the nearest day. Well, how long will it be? How large will it be after one day? We know if we start with 25,000 square meters and we add 2.4% of 25,000, we're going to get 25,000 plus 0.024 times 25,000. And just for the sake, I'm just going to go ahead and write this as 25,000 times 1 plus 0.024, which is 25,000 times 1.024. And this turns out to be, let's go ahead and see what we get. We get 25,000 plus 0.024 times 25,000. And you get 25,600 square meters. Okay. Now the reason why I wrote it like this is because if we were to do a second day, we would say, well, let's take the first day. And this is just a thought experiment. After 2 days, we'd say it's 25,600 plus 2.4% of 25,600, which is 25,600 plus 0.024 times 25,600. And you could calculate that, but I wanted to recognize that this is 25,600 times 1.024. And since the 25,600 itself was 25,000 times 1.024, we could see this as 25,000 times 1.024 squared. And you might notice the pattern. After 3 days, I'll go ahead and drop this down. Verify that we get 25,000 times 1.024 cubed. So after 1 week, I would say we're going to have 1.024 to the 7th times 25,000. And after 100 days, I would say we're going to have 25,000 times 1.024 to the 100th. And let's go ahead and calculate those. So to the nearest 10 square meters, this would be 29,510. So this would be and let's see what this one's going to be to the 100th. $267,880 to the nearest 10 square meters. And how long until the spill's doubled in area? Well, again, this can be done algebraically or graphically. The initial amount was 25,000, and we want that to grow to 50,000. That is double that by some power of 1.024. And we get 2 is 1.024 to the t. And if we take, for example, log base 1.024, log base 1.024 of 2 would equal t. And obviously that's the same as saying the log of 2 over the log of 1.024, or natural log. Okay, so let's go ahead and calculate this one. The log of 2 divided by the log of 1.024, and we get 29. Around 29 days is approximately 29 days. Okay, there we have it.